Okay, so the cache idea. How does this work? Well, of course, 100% of the time, the CPU is asking, certainly every cycle, for an instruction. And then we're going to look in the cache. And what we mean by look is, well, I'll describe that hardware in a moment. And alpha percent of the time, this is called the hit ratio, we hit in the cache, meaning the address that we're looking for is, in fact, the contents of that address are already in that yellow box. Okay, so, and the rest of the time is not there, and we have to go off and look in dynamic memory. And in fact, we can, using the access time of the cache, which tends to be on the order of, an instruction, the same sort of speed as the processor is executing instructions. Okay. And the access time for main memory, T sub m, which is often several orders of magnitude slower. What we want to do is to figure out what sort of hit rates do we need to get in order to get an average access time that's much closer to TC, the fast number, than it is to TM. Okay, so that's one goal, is to figure out what sort of hit rates we need and then wonder if we can build hardware that will get that hit ratio. The second goal, so we get a good average access time. And the second goal is to make sure that we don't, the programmer doesn't really have to bother their head about this, right? Because it would be awkward to have you think, not only you have to get the functionality right, but then you have to spend a lot of time worrying about, where in the memory hierarchy things are. So that's our goal. It's been somewhat defeated in recent years by the existence of multiprocessors, which have this problem in spades. If we have trouble keeping one processor fed with information from memory, imagine if you have 4 cores or 8 cores, and we have to keep them all fed from there. We have 8 hungry children all going, chirp, chirp, I'm hungry, where's the worm? And say, look, I can only get worms so quickly here. And so, in fact, in the modern world, if you want to build high-performance, multi-core applications, you starting to have to be more aware of the memory hierarchy than maybe we would like. Okay. So how high of a hit ratio do we need? Well, suppose we have, a 4 nanosecond cache memory and a 40 nanosecond main memory. If we want an average access time of 5, in other words, only slightly slower in the cache, you can see that we actually need a very high hit rate. Over 97 some odd percent of the time, when you ask for a location, the hardware has to say, oh, I've already got that. So keep that number in mind, and we're going to work on figuring out how to make that happen. The good news is that, remember that diagram where I showed the working set size, the number of locations sort of over a span of time, how it sort of went, there was a knee in that curve? The good news is that if we can sort of, so here's, there's the size of that working set, okay, as I made the delta t interval bigger, okay, sort of it flattened out. The good news is if I can build a cache that's big enough and that I can get all of these locations in the cache, I should expect a reasonably high hit rate, because that's all over a big span of time, those are the only locations I'll need that the CPU will be asking about. So you experience this a lot, right? When you first type Python, when you power on your machine and type Python, you can look there and you're sort of drumming your fingers and you're sort of going, this is taking a while, right? You Control C, you type Python again, and you get the prompt right away, right? So there's a lot of things that are happening when you first start up a program where things are being moved into faster locations of the memory hierarchy that the next time you use it, it turns out it's there, and everything is orders of magnitudes faster. Okay, so let's talk about this cache principle. And what I've done, so here's a little sort of a virtual thought experiment. So we have file cabinets, which are slow, and I've invited Clark Kent to join us today, Superman, to serve as our high-speed memory. And so it takes 5 minutes to look in the file folders, but only 5 seconds for Clark to say, okay, I have the information that you want. So I'm in the next room yelling addresses into my outside of my office door, and there's somebody out. So Clark is out there along with the file cabinets, and I say, "Bit diddle Ben, I want information." That's the address that I'm sending. And the algorithm is, well, Clark's going to quickly look to see if he happens to be holding what I need. In other words, is it in the cache? And if so, he can respond quickly. Okay. The difficulty, but then he has to go off to the file cabinet. And I'm hoping that we can come up with a scheme that when I'm yelling names out of my door, that mostly Clark will answer rather than the file cabinets. So that's what I want. And what I'm going to do for a few minutes is to sort of use this little thought experiment to explore the things that can go wrong with the scheme and see if we can figure out how to fix them. And then we'll look at some hardware.